Standard synchronous loops can be dangerous when processing massive datasets or infinite streams. This split-screen comparison shows why. On the left, a standard map function causes the memory profiler to spike and the UI to lock. On the right, a for-await-of loop processes the same data while keeping memory usage stable. The ability to manually control JavaScript's single-threaded execution flow is one of the primary markers of senior engineering. To handle data without crashing the environment, we use lazy evaluation. This allows us to process exactly one piece of data at a time, only when it is requested. We will build this model in 3 stages: the iterator protocol, the pausing power of generators, and finally, managing latency with asynchronous streams. Mastering these core concepts allows you to manually orchestrate how the browser handles memory and the call stack. We start by attempting to use a standard for-of loop on a raw, custom JavaScript object. The engine returns a type error stating the object is not iterable. By default, JavaScript loops do not know how to traverse custom data structures. They require a specific set of instructions. Those instructions are defined by the iterator protocol. This architectural contract decouples the shape of your data from how it is consumed. Like this mechanical arm, the loop doesn't need to know what is inside. It only knows how to retrieve one item at a time. You implement this contract by injecting the Symbol.iterator property into your object. This Symbol.iterator must return an object with a next method. Each call to next produces a strict payload, a value, and a Boolean named done. As the loop progresses, the value updates with new data, while done remains false. In the final cycle, the value becomes undefined, and done flips to true, signaling the engine to terminate the loop safely. Failing to return done true is a common error. Without that signal, the loop never terminates, creating a silent memory leak that can crash the main thread. This state machine is the foundation for native syntax. Operators like the spread operator rely entirely on these value-done payloads to function. Essentially, your iterables define what the data is, but your iterators define how the engine traverses it. Manually writing next methods and tracking internal state is verbose. We need a more efficient abstraction. The generator function, or function asterisk, provides that abstraction. It is a specialized syntax that automatically constructs the iterator object for you. The primary advantage of a generator is that it acts as a coroutine. It can physically pause its own execution frame in memory. Notice what happens on the call stack. When we call a generator, the block is pushed onto the stack, but immediately ejects a paused generator object and pops back off. When we call the next method, the execution frame jumps back onto the stack and processes code until it encounters a yield statement. The yield pauses the function. The execution frame physically detaches from the stack and is saved in the memory heap, leaving the main thread unblocked. This creates a bidirectional channel. The generator yields values out, and the caller passes new values back in. There is a specific timing mechanic here. In the expression let y equals yield 1, the number 1 is sent out to the caller first. The variable y is not assigned until a value is passed back in during the subsequent next call. Generators function as stateful coroutines, enabling the lazy evaluation of complex or even infinite sequences. Standard generators are strictly synchronous. They return their yielded values the moment next is called. If you yield a promise from a standard generator, the iterator returns the pending promise object itself, forcing you to manually unwrap it with .then on every iteration. This is inefficient for handling network latency. In this pipeline, the system must wait in silence for unpredictable data to arrive. Standard loops are not designed to bridge these gaps in time. The Symbol.async iterator protocol addresses this by modifying the state machine so that next returns a promise that resolves to the value done payload. We consume these asynchronous streams natively using the for-await-of loop. This diagram highlights the difference in execution. In the top timeline, running a loop over an array of promises triggers all network requests concurrently, crowding the microtask queue. On the bottom timeline, using an async iterable, the requests fire sequentially. The loop waits for one promise to resolve before the next one is even requested. This sequential approach prevents micro-task queue starvation and protects the browser's memory from being overwhelmed by incoming data. Async iterators combine the pausing mechanics of generators with the non-blocking nature of promises to handle infinite network streams safely. To categorize how JavaScript handles data, we can map the entire execution landscape based on time and quantity. This matrix organizes our mental model. Columns are synchronous versus asynchronous. Rows are single versus multiple values. For single synchronous values, we have standard functions. For single asynchronous, promises. For multiple synchronous, iterators and generators. And for multiple asynchronous, asynchronous iterators. This final quadrant is the backbone of modern APIs like Node's readable streams and the browser's Fetch API. These protocols provide direct control over the memory heap and execution thread. This technical depth is essential for building applications that handle data at scale.